This is the simple school spectrometer. From an arc struck between two copper electrodes, light passes through the collimator, prism, and telescope, and is converted into a copper spectrum. If the eyepiece is replaced by a camera, the instrument becomes a spectrograph, and the photograph which it produces, a spectrogram. A permanent black and white record, generally used in negative form, the spectrum can now be measured, compared, and preserved for use in later work. This is how a spectrograph works. Light from the source passes through a slit to the collimating lens, producing a parallel beam. On refraction through the prism, the light breaks up into its various wavelengths. The longer red wavelengths are refracted lengths are refracted most. These separated lines are then focused on the photographic plate. It's obviously desirable to separate the lines as clearly as possible. The resolving power of a prism increases with its size. With greater sharpness obtained in this way, the spectrum can be magnified more highly than before. The focal length of the telescope is therefore increased, and the resulting spectrum lines are much more clearly and widely separated. This is the arrangement of lenses and prisms in a medium-sized glass spectrograph. Collimating lens, prism, and telescope lens set in the heart of the instrument. Setting up a copper arc as before, the spectrogram now produced has lines with much greater separation. A wavelength scale, usually marked in angstroms, makes it easier to identify and measure wavelengths than with the smaller instrument. A glass optical system allows only the visible wavelengths to be recorded. But if the glass lenses and prisms are replaced by quartz, then the resulting spectrum is extended beyond the visible into both the ultraviolet and infrared, doubling the range of the spectrograph. Although quartz gives a larger range, it has a lower refractive index than glass, so its lines are not so widely dispersed. But the extra lines invisible to the eye can only be detected and recorded photographically. Spectrograms are therefore essential beyond the visible range. Many spectrographs are fitted with a device for comparing spectra. Sliding this Hartmann diaphragm across the slit, 3 spectra in turn are recorded. In the resulting spectrogram, the 3 spectra overlap slightly and can be easily compared. Often a standard element such as copper or iron with known wavelengths is recorded alongside an unknown substance to act as a kind of reference or measuring tape. In some instruments, a diffraction grating is used instead of a prism. Many parallel lines, several thousand to an inch, are ruled on a surface of glass or mirror. Gratings are sometimes operated in a vacuum to avoid absorption of ultraviolet light by oxygen in the air. In this and other ways, the outer limits of the spectrum have been extended in the ultraviolet to well within the X-ray region. And in the infrared, to overlap the region of short radio waves. For most analytical purposes, a range of 2,000 to 10,000 angstroms is more than adequate, and the quartz spectrograph is the instrument most widely used today. This particular type of spectrum is called a line spectrum. What causes line spectra? In the copper atom, 29 negatively charged electrons rotate round the positively charged nucleus. It is the behavior of these electrons, when excited as in the arc, which causes the characteristic lines in the spectrum. To see what happens more clearly, the orbits are drawn as if in one plane. It will also be easier to consider a simpler element, the simplest in fact, hydrogen, with only one electron. Although it's possible to imagine an electron revolving at random in any of an infinite number of orbits, it can in fact rotate only in those orbits with an energy level equal to an integral of Planck's constant h. These orbits, or stationary states, are grouped together in shells, or energy levels, which are lettered. There are no intermediate stages between these orbits. Like chessmen, the electrons must leap from one stationary energy state to another. In order to make an electron jump to a larger orbit of greater energy, it must be given a quantum of energy. This can be done by supplying energy as heat, as in a flame or arc, or electrically, as in a spark or discharge tube. When the electron returns to the smaller orbit, it will give back the same parcel of energy which it received, emitting a quantum of monochromatic light or photon of frequency nu, such that h nu equals E double dash minus E dash. It has been possible to make calculations linking particular orbital jumps with the lines in the hydrogen spectrum. The colors of the different frequencies mingle together to become the characteristic light of that element when excited. For example, the pinkish blue of hydrogen, the green of copper, the yellow of sodium. The spectrograph then breaks this combination down into its component wavelengths, so that the series of lines in a spectrum, monochromatic images of the slit, denote the wavelengths which belong to each element. Like fingerprints, no two elements have the same spectra, nor do they share wavelengths, although some are very close together. Another class of spectra are band spectra, caused by molecules. The nitrogen molecule, which gave that spectrum, is being excited in a vacuum tube. A large and powerful instrument like this will produce spectra with high resolution, in which it can be seen that the bands are actually a great number of fine lines very close together. A molecule has three types of energy: the rotation of its electrons, the vibration of the nuclei, and the rotation of the nuclei. When a quantum of energy is absorbed, the electron jump is accompanied by change in vibrational energy and change in rotational energy. This builds up the band spectrum characteristic of molecules. Analysis of a band spectrum gives information, therefore, about the structure and bonding of the molecule. The third type of spectrum is the continuous spectrum, whose source is usually the white light from incandescent solids or liquids. In a hot solid, atoms and molecules have little room to move. Any radiation of definite frequency which they might emit is altered by collisions with neighboring atoms. The resulting spectrum is rarely an infinite number of overlapping images of the slit. Line, band, and continuous spectra are all emission spectra. If white light is passed through certain gases and solutions, in this case a sodium flame, before reaching the spectrograph, a change in the continuous spectrum can be seen. The continuous spectrum of the lamp itself, the continuous spectrum after the light has passed through the sodium. A dark line has appeared, indicating that a wavelength has been cancelled or absorbed. The white light, in fact, is acting as another exciting agency. The light containing all frequencies falls on the sodium atoms. These are unaffected by any frequencies except those which correspond to their own natural transition, which they absorb and radiate back again. This re-radiated light is scattered in all directions, while the unabsorbed light passes straight through with unaltered intensity in its original direction. Virtually none of the absorbed light reaches the collimator, thus producing an absorption spectrum. Comparison with the emission spectrum of sodium shows that the missing line in the yellow is exactly the same wavelength as it would emit when excited. The solar spectrum is an absorption spectrum. The absorption lines, often called Fraunhofer lines after their discoverer, indicating those wavelengths which have been absorbed by the chemical elements in the sun's atmosphere. Flame, the simplest method of excitation, gives good results in the visible and near-infrared. It is often a Bunsen burner flame, but an oxyacetylene flame is used in Lundegaard's method. A solution of the sample is atomized into the flame, a method especially suitable for biological materials such as plants and soils. Arcs, a convenient way of handling metals, produce good ultraviolet spectra, the region where most characteristic lines are found. Arcs give high sensitivity for qualitative analysis, as in the analysis of these samples of copper for traces of unwanted elements. The resulting spectrogram is projected and enlarged. The upper spectrum is of very pure copper, but traces of impurities such as tin, lead, and magnesium have contaminated this lower sample. Sparks provide a steadier light source than arcs and are generally used for quantitative analysis. The density of spectrum lines is measured in a microphotometer by a photocell. Lines of unknown quantity are compared in density with standard samples of known composition. Absorption spectroscopy is used increasingly in those industries interested in the molecular structure of materials. Two cells are prepared, one containing the sample in a non-absorbing solvent, the other the solvent only. Each cell in turn is placed in a beam of ultraviolet radiation of one particular wavelength, which is selected by turning a graduated drum. A photocell measures the amount of ultraviolet radiation transmitted and registers the difference in absorption between the sample and the solvent. The problem here is to determine whether any benzene is present, and if so, how much. A continuous recording spectrograph scans the wavelengths automatically, and the absorption spectrum is drawn by a moving pen. The characteristic trace indicates the presence of benzene, and the amount is calculated from the height of. During experiments, the material is likely to change fairly rapidly. The sample flows through a transparent cell, and its infrared absorption spectrum is the operator can immediately notice a change in the trace and so keeps a check on the composition of the material at various stages of the process. In foundries, where there are many different types of alloy in continuous production, it is an enormous saving of time and material to analyze the melt before it is poured. A small sample is cast and taken to the laboratory for analysis. In the direct reading spectrograph, the photographic process has been eliminated, and quantitative analysis is done automatically by photocells. When the sample has been trimmed and machined, it's sparked for a fixed period, during which each photocell measures the brightness of its spectrum line. The information is fed to the recording console, which measures and records the quantity of each element in turn. The analysis, which would have taken at least 2 or 3 hours by ordinary chemical methods, is complete in 5 minutes. With this check, the pouring can begin. Aluminium of known composition, ready to meet the very exacting specifications of modern industry. The spectrograph is also used in biological research. The yield of crops and the health of grazing animals depends in large measure on the nature of the soil which supports them. The soil, and not only the surface soil. Samples are taken from different layers right down to the parent material. From these samples, dried and finely ground, solutions are prepared by a kind of leaching, which indicate the chemical elements which would be available for absorption by the plant roots. Lundegaard's method is used as it's specially sensitive to the elements most likely to be found in soil analysis. In criminal investigation, the specimens to be analyzed are often minute and hard to identify. In this factory robbery, the thieves had left hardly any trace. A metallic stain on the door plates and a graze mark on the posts. Not a great deal to work on. However, sometime later, when examining a car under suspicion, police found a likely-looking jemmy and a dent on the wing. It seemed a possibility. A possibility confirmed by the examination of the resulting spectrographs. A match between the jemmy and the stain on the door plates, post and car wing, sufficient evidence that this was the car involved in the robbery. Works of art, like criminals, must be assumed innocent until they are proved guilty, assumed genuine until they are proved fakes, and treated with respect accordingly. This small statue of a Greek god had a surface appearance which made experts doubt whether it really was ancient Greek, dating from 600 BC. The spectrograph is particularly useful in solving this sort of problem, for it can work with minute samples where other methods would be likely to cause serious damage to the object. A tiny scraping, barely visible, and taken from an inconspicuous place is sufficient for the spectrograph. These telltale lines of zinc, never refined before the Renaissance, cannot be more than 500 years old. It has a very special position in astronomy, second only to the telescope. In this spectrograph, the largest in this country, the whole building is the spectrograph. The sunlight is reflected by these mirrors to the grating nearly 100 feet away. With a powerful source of light like the sun, it's possible to use a condensing lens of great focal length in order to get a larger image of the sun onto the slit. Sunlight passes through the slit to strike the plane grating mounted 30 feet away. The grating produces a complete solar spectrum over 20 feet long, with thousands of absorption lines providing data about the sun. For example, these spectra are of the left and right edges of the sun. The shift shows the Doppler effect due to the rotation of the sun. The left edge approaches while the right edge recedes. In a similar way, the composition, temperature, and motion of the stars can be determined. It is information obtained by the spectrograph discoveries.